All right, today in 5.4 we are using graphs. Our objectives are to draw and interpret graphs representing real-world relationships. Okay, so you will often need to draw or interpret graphs that model real-life situations. Okay, we call this mathematical modeling is when you do that. Or you're going to see them a lot. When you become an adult and you're reading a magazine, different things, you're going to see a lot of different mathematical models. Okay, so you want to be able to read those and interpret them, understand what they're saying. We've talked about this a little bit. Our horizontal axis, or the x, is always our independent variable. Okay, that's the x-axis. Your vertical axis, or your y, is going to be the dependent variable. Okay, so if you look at these two graphs that we have, or well, if we look at the table first, we have this table that has a title, growth of a largemouth bass. Okay, this is our graph of that, has the same exact title, growth of a largemouth bass. Okay, now when we look at this information, we need to know which thing is independent, which thing is dependent. So we have the age in years and the length in inches. Okay, our age in years is our x value. It's our independent variable. Okay, it's the thing that we are looking at first. And so notice that goes on, since it's our x, okay, value, it goes on the x-axis. Okay, it's our independent variable, which is different than our length, okay, in inches. That's our y value, and it goes on our y-axis. Okay, and then otherwise, each of these is an x-y pair. So we would be graphing 1, 6.5, 2, 11. So that's what these points, 1 and 6.5, 2, 11. That's what those points are. Okay. Now, the next thing we're going to do is it says draw a smooth curve to connect the points. So approximations and predictions can be made. So we want to draw a smooth curve. A smooth curve. Notice we're going to start at 0, 0 here and just do a smooth curve to kind of connect those points. All right. And I guess I should have, it looked like they went longer. It's okay, I went a little further than I needed to. All right, well, now that we do that, we want to make, the whole point was so we can look at some approximations and predictions. Okay, so it says predict the length of a 1.5-year-old bass. All right, so to do that, I'm going to go down here to my age in between 1.5, and I'm going to follow it up, and it lands right about there. And that number, what is that number then? What is that number that you would consider that? Can you tell what that prediction would be? It's about 9 inches, right? I would say that's about 9 inches. Good. It's a little hard to see sometimes in this graph. Hopefully I gave you time to do it on your own. All right, so then it says, well, about how old is a 15-inch bass? Okay, well, in that case, we need to go over from 15. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, I think is this number here, right? So if I follow that over and then I follow that down, where does that put me? In between 3 and 4, so 3.5. We could say 3.5 years. Okay, because we know that this is in years. All right, so we're just using this information to model and make predictions. Okay. All right, so let's clear this up and go to example 1. All right, example 1 says model the first class postage rate data given in the table and state the general characteristics of the rate of increase of postage over the years. This kind of affects us now, right? Postage just went up this year. Predict what the postage rate will be in 2050. All right, so if you notice here, I have taken the tables, okay, that were given to us, and I went ahead and copied the graph and put it in there. Okay, so we could save a little bit of time in doing that. That maybe would have been something that we could have done, but we didn't. Again, saving some time there. Okay, so we have modeled the table into this graph. Okay, so now we want to state some general characteristics of the rate of increase of postage over the years. So what are some general things that you could say? I mean, it could be even like which one of these is independent, which one is dependent. Okay, so independent is the year, right? Because it's on our y-axis. So our dependent element here or thing is what? Should be vertical. Okay, so that is the stamp cost. So that's our stamp cost. Okay, so that is a characteristic you can start with, like just listing some things. How about if we kind of connect those dots like we talked about, or I showed you on the first one. If we connect the dots, what do you notice? So I see something different from here to like here. Okay, so what could we say there? All right, well, we could say that it maybe in the early years or 1850 like to 1950 something. So the first 100 years, whatever. So we could say in early years, postage rates or cost, okay, either of those, were steady. They didn't change. We could put unchanging if that helps. Okay, so in the early years, postage rates were steady. They didn't really change. All right, then what can you say from here to there in, I don't know, what is that, 2010, 2012? Okay, we definitely see an increase, right, from here to here. So we could say after the first 100 years, you could say in recent years, however, okay, the rate, what has it been doing? Have increased. Okay, the rates have increased. Is it a little bit? Is it a lot? Is it dramatic? Is it whatever? You know, like however you kind of want to describe it, if you think that this is, like this is, do you think that's a little increase? Has it been a drastic increase? It's pretty drastic, right? So after the first 100 years, the rates have increased drastically. All right, good. Then predict what the postage rate will be in 2050. Okay, well, in order to do that, we have to continue this increase. Okay, we have to continue that increase. And then we need to look at where it would be in 2050. So if we follow this up to here, right, and then we follow that over, I'll do my best to keep my line straight. It's kind of hard there. What do you think? I have about, oh, nope, I got off on my line, didn't I? Yeah, I came down. It should go up here a little bit. I came down on my line, which would be about 80 cents. So in 2050, we would expect or predict the cost to be 80 cents, okay, to mail a letter, which we're getting close, I think, right now, where we just went up to 68 cents, I believe. Okay. All right. Very good. Example 2 then says use the distance time graph to answer the following questions. All right, let me erase some of my writing here. There we go. So it's not in the way. All right, so use the distance time graph to answer the following questions. How far has the skydiver fallen after 10 seconds? After 10 seconds. Okay, so again, we need to look at our time. We're going to have to draw some lines. So here's our 10. Okay, and I apologize. It is really hard to do on the board, those of you that have written on the board. Okay, so what's it look like? After 10 seconds, he's fallen about what? What do you think there? It kind of looks like, see, I got a little off on my 10. I'd say if you have 1,300 to 1,500 feet, I would take that. Because my graph is not the best. All right. How long does it take the skydiver to fall 2,000 feet? Okay, I would be, so I've got 500, 1,000, 1,500, 2,000. So let's see. If we go there, and then go down from there. All right, so we're trying to track that and show you a little bit. How long does it take the skydiver to fall 2,000 feet? What do you think? So they're falling from 2,000 down to, what is that? What do you think? 14? It's not quite 15, so like 14 seconds? Yikes. It's crazy. All right, C. Describe the fall of the skydiver in the first 5 seconds, the next 15 seconds, and the final 10 seconds illustrated. Okay, so to do this, I'm going to erase these lines that we have, and let's mark our 5-second intervals. Okay, so we've got, so our 5 seconds would be here. Okay, then it says so the first 5 seconds, the next 15. So that's going to be from 5 till 20, right? Because we've got 5, 10, 15 seconds. And then it says the final 10 seconds. Okay, so this is the 5 second. There's 15 seconds in here, and there's 10 seconds in there. All right, so we want to break down our description right there between those 3 places. Okay, and maybe I'll erase my line a hair so you can kind of, I'm not quite covering it. Maybe you can give a better description of what's happening. Okay, so how about that first 5 seconds? What's happening in this first 5 seconds? What do you think? There's a little bit of curve to that, it looks like, right? Like he's speeding up, maybe. So, I mean, you could say he's falling quickly. Maybe he's falling faster since this has got some curve to it. And it's not a steady climb. Like this one was really straight and steady. This one's got a curve. Like if I made that bigger, it would look like a curve. So it's getting, really this is showing that he's falling faster every second. Okay, so we could say he is falling faster every second of the, let me erase that. So he's falling faster every second of the first 5 seconds. Okay, then let's look at my next section. What would you say about this section from here to here? How would you describe his falling? That's pretty steady, right? Okay, so then we could say he is falling at a steady rate for the next 15 seconds. So he's falling at a steady rate for the next 15 seconds. All right, and how about that last section? How about our last section? And let me see if I can move my screen down just a little bit. There we go, so I can keep writing. How about our last section? What would you say there? It's becoming a little bit flatter here, right? Kind of leveling off, which means what? Okay, he's slowing down. He's falling much slower rate. And it's more constant because it's leveling off. So the last 10 seconds, okay, so the last 10 seconds, he's falling much slower. So much slower and more constant. Okay, so much slower and a more constant rate. Okay. All right, so hopefully you're just talking about these is helping you see a little bit more about the graphs. All right, then we have some other graphs that are really cool. Okay, so these graphs are without numbered axes. So graphs without numbered axes can be drawn to illustrate the relationship between variables. This graph illustrates the relative speeds at which the skydiver falls. So notice we have the time and the speed. Okay, so we have the time and the speed. A description of the graph would indicate his speed is increasing as he falls. Okay, so this is his time. So you have to think of skydiver. Okay, and this is time. So he's currently in the plane down here, right? He's in the plane. This is not his speed of the fall. He's just in the plane. He jumps out of the plane and his speed increases rapidly, right? Would indicate his speed is increasing as he falls. Then, okay, he reaches a constant rate of speed or a constant speed as he's falling. So when he first jumps, right, he's getting faster and faster and faster and faster. And then it's like, oh, I've kind of got as fast as I can go. He's just going to keep falling at this steady rate. All right. Then his speed rapidly decreases. I tried to change my color. His speed rapidly decreases after he deploys his parachute. So this right here is that moment that he pulls the string, right, pulls the ripcord and puts on or releases, opens, deploys his parachute. Okay, so then he starts slowing down. His speed is slowing down and he's falling at a slower constant speed, okay, until he comes here. So he pulls the parachute and then he hits this slower constant speed. So that's some things to notice. These flat places are, like here in this case, it's a constant speed, just like up here, right? This one is a constant, and we're talking about speed. So it's a constant speed. Okay, so let's try to do example 3. Okay. The key to these is always really paying close attention to what your variables are. Example 3, the Wadsworths, so this is a family, so the Wadsworths spent a day hiking in the mountains. Mrs. Wadsworth's GPS-enabled sports watch records her altitude, so we're checking out altitude. Analyze the following graphs produced from their trip to describe their hike during each period of time. So if you look at these, okay, we have a little bit of difference. We have the time here and her heart rate. And this one is the time and the altitude. So we want to analyze the following graphs. Okay, so both of them. Produced from their trip to describe their hiking during each period of time. So you'll notice that we have the same periods of time. Okay, so we have A, and then we have B and C. So we're going to try to figure out what's happening during each period of time. So let's look at A. Her heart rate is really high, okay, but constant. We know that this is constant. I'm going to label that constant. And then if we look here, all right, A stops. Let's see. Oh, so sorry. I stopped lower. So there, if we look at her altitude is rising. So what can we say about this time period of A? Well, her heart rate, we might say, is elevated or high. So her heart rate is elevated as what is she doing? If we look at her altitude is increasing. So what is she doing? Okay, she's climbing, or she's climbing up a slope, or she's ascending. But her heart rate is elevated as she is climbing higher or up, however you want to do that. But her heart rate is elevated as she's climbing higher. We'll go with that one. Okay, then let's look at B. Okay, so for B, man, check out this heart rate, right? The heart rate drops, and then it's down here lower. Okay, and B, with her altitude, that's constant. Okay, so both of these, here it's constant, her heart rate is constant, and here the elevation or the altitude is constant. But don't forget that we had this huge drop in her heart rate. So what would you say for B? Okay, we might even, like, we could say her heart rate decreases, and we might even say, like, maybe this is normal, right? She has to have a heart rate, so we could maybe call that normal. But we could just say her heart rate decreases, and while they what? Where do you think her heart rate decreases, or returns to normal. We could say returns to normal if we want to call that normal. So her heart rate decreases or returns to normal as she, okay, for elevation is constant. Maybe she's walking around the top, like on the peak of the mountain that she's on. Maybe she's looking around and taking some pictures. We just know that her elevation is constant. So her heart rate decreases or returns to normal as she walks around the mountaintop. So the mountaintop. Because we don't know all the answers, right? We're just kind of trying to paint a picture of what's happening. Okay, so C, if we look at her heart rate increases, and then it's constant again. In C, her elevation is decreasing. All right? So in C, we could say, so we look at her heart rate is elevated, but it's elevated to here. Is it as high as it was up here? No. So we could say her heart rate is elevated or raises. I'm going to try to use some different vocabulary than sometimes you maybe always use. So her heart rate is elevated as she, okay, and we look at her altitude. What's she doing? All right, she's climbing back down, right? She's maybe not going all the way to the bottom of the mountain, but she's climbing down part of it, or she's descending. So her heart rate is elevated as she climbs or hikes down the mountain. Awesome. Okay, then let's look at D next. All right, so we look here. Oh man, her heart rate really went up, higher than the first one even. And what is she? Let's take a look at her altitude. My goodness. Okay, so her altitude has increased again there. So what's happening? Her heart rate has jumped. Okay, her heart rate jumped. We could say raised, whatever. Her heart rate jumped as she climbed. What do we think? Oh, you know what I can tell if I look at these? Okay, if I look at, I wish I had you in class. If you look at the steepness of her elevation, right? This one is going up, but this one is a steeper elevation. Let's see if I can trace this and move it over. So if I trace that in black, let me see if I can then move it. Sometimes you can get those and move them. Oh, it's just going to move the whole thing. That's not what I want. So never mind. Cancel that. It doesn't want to cancel. Okay, there we go. So I was say, but this one is a steeper incline, which means the mountain is steeper. So her heart rate jumped as she climbed a steeper mountain. All right, let's look at E then. Okay, E, her heart rate drops drastically and then becomes constant. And E, her elevation is constant. So what's she doing? It's just like B, right? Her heart rate decreases as she walks around the mountaintop. All right, so her heart rate decreases as she walks or rests or whatever, walks around the mountaintop. All right, and we have one more to do, so let's go back to blue. So for F, all right, we notice that her heart rate increases and then is constant again. And we look at her altitude, and what's she doing? She's climbing down the mountain, okay, or she's hiking. So we could say as she hikes down the mountain, her heart rate raises slightly. So her heart rate raises slightly. All right. So there you go. It's kind of fun to look at these graphs and to try to figure out like what is happening in time. I love when I have, especially when I have two graphs to compare. I feel like sometimes it's easier to make sense of what's happening when you can see the heart rate and the altitude or some other thing. Sometimes maybe it's the heart rate and the distance that they're running or different things. But sometimes having more than one graph gives you a better picture of what's happening. All right, so that will be your homework. Will be based off of this stuff tonight. We'll see you later.